Let's run through a few examples where proxgrad in the dual is useful. So first example is norm regularization. We've seen this problem in a number of contexts. The primal problem is to minimize f of x regularized by some norm. I'm not going to assume it's a one norm or a two norm or anything in particular, which means that we expect to see results that have a dual norm somewhere in there. Minimize f of x plus ax minus b. Again, this is exactly in our f of x plus g of ax framework. Our dual is maximize minus f star of minus a transpose z minus b transpose z subject to the dual norm of z less than 1. How did this happen? Again, think about what g of x is, and then think about what its dual would be, and then you'll see that this is what comes out. So again, all of these good exercises that I expect that you should be able to do. So let's suppose in this case, so that we can directly apply proximal gradient, that f is strongly convex and that therefore f star is smooth. So let's suppose f is strongly convex, hence f star is smooth. So we're going to do dual prox gradient. And what is our prox function going to be? In order to write this exactly in the form of f star plus g star here, our g star is going to involve an indicator function. And going back to the first time we introduced prox, and in particular proximal gradient in the primal, we saw proximal gradient as a generalization of projected gradient, exactly because the prox function of an indicator function, in this case the indicator function of the unit ball in the dual norm, is going to be the projection onto that unit ball. So we get x hat is equal to minimization of the Lagrangian, the argument of the Lagrangian, f of x plus zt times ax, and then zt plus 1 is going to be the prox with respect to g star. We don't need the Moreau decomposition in this case because the prox of g star being the indicator function of the dual norm, is straightforward. It's just projection. So we're not going to use Moreau decomposition, and zt plus 1 is going to directly, we can write it as the projection over z star less than 1 of zt plus lambda of ax hat minus b. So this is my gradient step inside the parentheses with respect to f star, and then with respect to f star minus b transpose z, and then the proximal function of the indicator of the dual norm is just projection. Okay, let's see another example. It'll be similar in flavor, but in a way dual to this. So minimizing f of x plus now the sum of many norms. Let's just write just write the two norm. Okay, so let's think about how we're going to do this. So this is so the dual again is maximizing minus f star of minus b1 transpose z1 minus b2 transpose z2. I've got p of these, so I therefore have p dual variables z1 through zp. Each one of these a vector, subject to a dual norm constraint. Since I wrote down the two norm, recall, is self-dual, and therefore my constraint is that each of the zi's is in the unit Euclidean ball. In this case, exactly what we saw before on the previous slide, we find that x hat is a solution to the Lagrangian argmin of f of x plus sum of bi transpose zi times x, and each individual zi is projected onto the Euclidean, is a projection onto the Euclidean ball. So the zi t plus 1 is equal to the projection onto the Euclidean ball and the unit norm of z plus lambda bi of x hat. So if f has further separable structure, then again note that this argmin, if f has it, then we could take advantage of this. Okay, a related example is one of the first types of problems that people begin to be interested in with respect to splitting methods. So the basic problem, which we'll look at, is you have some number p of convex sets, for example unit balls or Euclidean style balls or maybe norm balls, where projection onto them is easy. And what I want to know is how to project onto their intersection. So a natural idea for projection or even finding a point in the intersection of convex sets is maybe I do something like alternating projection. If you'd never taken this class, maybe this is an algorithm that you would have thought would be a good candidate algorithm. Project onto one, then project onto the other, and somehow try to combine these. So this is that kind of proto-algorithm that you would have come up with is exactly illustrating this idea of divide and conquer, namely trying to deal with the individual functions that we have separately. This is, in a way, the entire agenda of looking at these operators. Of course, we're looking at them in much more detail and looking at them specifically. So let's look at the overall problem that encapsulates the problem of finding a point in the intersection of convex sets or projecting onto the intersection of convex sets. I just want to minimize a convex function subject to x being in C1 and C2 and up to CP. Part of the exercise that I want to do here is, again, just getting practice of seeing how this naturally fits into the framework that we've been discussing. So that when you have types of problems like this, you should naturally consider the dual algorithms as a candidate approach to what you're trying to solve. So to put this into our general template, we need minimize f of x plus g of ax. So what's g going to be here? G of y1 to yp is going to be the indicator function of c1, y1, plus the indicator function of c2 plus the indicator function of cp of yp. And if I want to write g as a function of a single variable, like g of ax, I would so recall I want g of ax. So what's a going to be here? A is just going to be copies of the identity. I'll write id just to make sure we're not confusing this with the indicator function. So this is a. So recall, how do I get the dual again? I have f of x subject to this constraint. If I write, I can write this certainly as minimize f of x plus g of ax for this x. And then the way that if we wanted to derive the dual from scratch for this particular example, you would write down y1 is equal to identity times x1 times x, y2 is identity times x, etc. And then dualize those equality constraints, and then you get the dual. That's essentially what we've been doing. And if you do that, you find that the dual in this framework is to maximize minus f star of, I'm going to have, again, p dual variables now, minus z1 minus z2 minus zp. This is basically my minus a transpose times my dual variables. Minus the sum of the dual of the indicator variables at the indicator functions of ci. So again, I'm going to assume that f star is smooth, or equivalently that f is strongly convex. And I want to do dual prox gradient, so I now need to find what is the prox mapping of this sum of indicator functions. So here is a good opportunity for us to use the Moreau decomposition. So we're going to use that the prox of lambda times one of these, the dual of these indicator functions. So again, note that I'm not taking the prox of the indicator. That's what I did in the previous example. And the prox of the indicator is projection. But now I have the prox of the dual of the indicator. But using the Moreau decomposition is going to get me back to using projection, because the Moreau is going to relate the proximal operator of the dual of the indicator to the prox of the indicator, which is projection. And so recall that using Moreau, this is equal to just z minus lambda times the projection onto ci of z over lambda. Okay, so let's write down now what our overall algorithm is, and let's also so in this case now, finally we've got that my proximal gradient algorithm. So let me, just as a matter of notation, let me let z bar be the sum of the zi's. And then z I t plus 1, the way that I update the ith component, this is going to be equal to zi plus lambda times the gradient of f star, remember it's smooth by assumption, evaluated at minus the sum. I'll just use my notation above, minus lambda times, let me move this down just a bit, minus lambda times the projection onto ci of zit divided by lambda plus the gradient of f star of minus z bar. Again, what's happened here? Zt plus 1 should have just been the prox, but I used Moreau, so it's equal to z plus the prox, or the argument of the prox plus the prox of what would have been the primal function. The primal function was an indicator, so that's where this projection comes from. You can see that this is essentially the pattern. Moreau tells me that instead of having the prox of the whole thing, I have the argument plus the prox of the dual, which is the prox of the primal. And therefore, my algorithm now, what is missing? I just need to write down this, but this is our familiar thing, which is going to be the minimization of the Lagrangian. So the gradient of f star of minus z bar is equal to x hat, which is going to be equal to the argmin. Again, remember, assuming strong convexity of f gives me smoothness of f star. It also gives me uniqueness of this argmin, which is why I'm writing equals throughout, of f of x plus the sum of zi, or z bar, transpose x. And then zit plus 1 is just what's written above. Let's finish by just seeing a special case of this where I'm doing projection onto the intersection of CIs. So what that basically means is that f is just equal to 1/2 times x minus y, subject to x in the intersection of the CIs. I'm projecting y now using Euclidean projection onto the intersection of the CIs. And we write down exactly what we had on the previous page, and except now the gradient, the Lagrangian step is going to be easy because f is this quadratic, so I can solve for that explicitly. So the Lagrangian step is going to be writing z is 0 if I'm actually solving that, is equal to x minus y plus the sum of zi's. And all I did is I actually just minimized this, where f of x is equal to 1/2 times the Euclidean norm. So in other words, x hat is equal to y minus the sum of zi's, and zi t plus 1 is equal to zi plus x hat over p minus 1 over p times the projection onto ci of p times zit plus x hat. What did I do? I took step size equal to 1 over p. A simple transformation to let us see this algorithm a little bit differently, perhaps a little more familiarly, is let's write wi be a scalar multiple p times zi, and then our algorithm of projecting onto intersection of convex sets says let's let x hat equal y minus 1 over p times the sum of wi, where each wi, oops, and there should be a t here, is updated as wit plus x hat minus projection onto ci of wit plus x hat. So you see that this is a way we're projecting onto each individual CI separately. So assuming that projection is easy, you're doing those projections separately and then combining them to form x hat and combining them to form the next t plus 1. So those are a few examples, and it's useful to have these, and we will pick this up next time as we move on to other splitting algorithms.